Hello and welcome to Math 252, Calculus 2 here at Cañada College. My name is Ray Lapuz. In this video, we'll take a look at checkpoint 4.8. Here, they want us to create a direction field for the differential equation, and the differential equation is given to be y prime is equal to x plus 5 times y plus 2 times y squared minus 4y plus 4. They want us to identify equilibrium solutions, classify them as stable, unstable, or semi-stable. So before we get to the plotter, I just want to do some quick analysis based on this differential equation, and we can try to anticipate what will happen. So if we take a look at this differential equation, we set this equal to 0 generally, so that we can find our critical or our equilibrium solutions. And we're generally looking for y values that are that would make this equal to 0. So y plus 2 equals 0, and I'm going to rewrite this because it looks like it could be factored to be y minus 2 quantities squared. So out of these two factors over here, we have y equals -2 would be a candidate for an equilibrium point. Y is equal to +2 would be a candidate for equilibrium points. Okay, the x plus 5, setting that equal to 0 will show us something kind of weird happening when x is equal to -5. But I don't think it'll play much of a factor in our equilibrium point analysis. So let's get to the slope field plotter, and you can just Google it. There's a lot of different slope field plotters out there, and here is one that I just saw. And so we need to input this equation. I think it was x plus 5, and then y plus 2, and then y squared minus 4y plus 4. Let's go ahead and graph that. Actually, there's a general solution that they're giving here, but let's not do a general solution because we don't need it. So it looks like my graph goes from -2 to 2 in the x, -2 to 2 in the y, so we clearly want to adjust that. Be nice if we can zoom in with just like your mouse or something, but here they have a formatting axis. I also want to include the -5 just to see what's kind of happening there. So maybe I'll go from -5 to 5 for the x. Actually, let's go larger. Let's go -10 to 10 for the x. And then for the y, let's make sure that we're including those critical, those equilibrium points. So 4, 5, or 6, maybe -6 to 6. It looks like this is kind of hard to see. We're expecting something at 2 and -2. So let me adjust this to be 4 to 4. So I think that analysis in the beginning makes us anticipate what we should be getting. If we're not getting it, then maybe a small adjustment. So now at -2 and 2, when y is equal to -2 and 2, you can clearly see this horizontal line over there, and that acts as an asymptote to any of the possible solutions. Maybe 10 is a little too far. Let's cut that down to 6. So we still see the disruption that's happening when x is equal to -5, but we can see from there, we can see what else is going on. So let me capture this and put it in our notes. And get a better analysis with that graph. So with this graph here, looking for equilibrium solutions, if we choose a starting point that is less than -5, then things might happen. It might go up. But more importantly, if we choose a value, an x value, a starting point value that's bigger than 5, and let's choose one that's bigger than y is equal to 2, so somewhere up here, you can see that it kind of takes off, and regardless of where you are, it looks like it's always going to be taking off. I mean, steeper than what I can draw right now. So it looks like we're pulling away from y is equal to 2. So let's make y equal to 2 here as one of the equilibrium point. Y is equal to -2 is another equilibrium point. And then we can see from one side it's pulling away. Now from the other side, if we choose something over here, it looks like it'll shoot up and then it'll use that as an asymptote. In fact, it'll come back down here. If you go on the negative side, it looks like it'll follow some sort of kind of logistic model. Again, my drawing is not very accurate, but that's kind of like what's happening. So for 2, we got above it, we got something that's pulling away, and below it, we got something that's approaching it. So this is what we would classify as semi-stable. Semi-stable. Because it's not approaching it from both sides, and it's not pulling away from it from both sides. All right, now let's take a look at the values if we were below -2. So if we were to choose a value that's below -2, it looks like up here it'll go up, but then it comes back down again. So if we choose any other point, it looks like it'll be going down. So let's choose a point over here. It looks like we're going to be going down. So now if we look at it from above, it looks like it's going away. If we look at it from below, it looks like it's going away. So this scenario makes -2 unstable. Unstable equilibrium. Okay, and I think that's it. So we found the equilibrium points, we classified them, and we have the plot of the graph. All right, I hope that helps.